Welcome back to part 2 of chapter 3. Okay, so part 2 of chapter 3, we're really going to get into projectile motion. Before we get there, I want to take a real quick backwards step for a second and just look at an example of an object on a ramp. So we're going to see a lot of things where we're no longer just on a flat surface, where we're now going up and down as well as side to side, because you're on a slope, an inclined plane, or a ramp. So in this case, we're trying to find the height gained on a slope. A car drives up a steep 10-degree slope at a constant speed of 15 meters per second. After 10 seconds, how much height has the car gained? Okay, so I'm going to start with my change of y, right? I need my height gained. I'm given the angle of 10 degrees, and I'm also given a velocity, and it's not a velocity horizontally or vertically, it's just the total velocity on the slope at 15 meters per second and a time of 10 seconds. Okay, so I would start by sketching this one out. I know that the ground is flat, it's going up a 10-degree slope, something like that. There's my 10 degrees, and everything's happening on the actual hypotenuse. So it's going at 15 meters per second, and my question is, what is my change of y there? So first, I would figure out how far it goes up the ramp. This is a pretty simple one because I know that velocity is equal to the change of distance over the change of time. And I'm intentionally not using x or y here because in this diagram, x would be the horizontal and y would be the vertical. So I'm going to call this distance along the top just d for distance. So I'm going to use the change of distance over the change of time. When I solve for the change of distance, that makes it velocity times the change of time, 15 meters per second times 10 seconds gives me a total of 150 meters. Okay, so I've got 150 meters is along my distance. Now, basically it's just a trig function. So now I have to separate it into its vertical and its horizontal components because I'm looking for the height that the car gains. So now I have 10 degrees and I'm looking for my y. So I know for my trig functions, the y is the opposite. So sine is opposite over hypotenuse. Sine of theta equals opposite over hypotenuse. Sine of 10 degrees is the opposite, that's the delta y, over my hypotenuse, which was 150 meters. Multiply 150 meters by both sides so that it converts to 1. And I'm left with delta y equals 150 sine of 10 degrees. Plug that into my calculator. 150 sine of 10. And I get 26 meters. Awesome. So just to kind of focus there, the key here is breaking it down into its horizontal component and its vertical component. We can call the horizontal component the x, the vertical component the y, and you can use this for lots of more complex kinematic equations as well, like the ones that are on your physics cheat sheet from the AP, especially those first 3 up at the top. We could plug in any of these 3 as well. In this case, it was just a distance over time, so you're good there. Okay? All right. So let's step back then and talk about projectile motion. So when a ball or any object is put into projectile motion, it has both horizontal and vertical components of the motion. In this case, the ball starts with a vertical upwards motion, and there's a horizontal component. So remember, the horizontal component, as we've previously mentioned, is going to be the same every time. That much, that much, that much, that much, that much. You'll notice that all these arrows are the same size, and they end up getting you to the vertical part. All right, if I'm drawing my arrows correctly. Now the vertical part keeps changing, right? The vertical component of velocity keeps changing. However, the acceleration is always the same. The acceleration is always downwards, and the acceleration in this case, because it's a ball tossed on the earth, would be negative 9.8 meters per second squared. So the acceleration in the y direction is equal to the acceleration due to gravity, which is negative 9.8 meters per second squared. So acceleration is always, always, always down. However, the velocities are always changing, right? The overall velocity is shifting. The horizontal velocity remains the same. Here's my horizontal velocity, always 10 meters per second. In this case, it was just set at 10 meters per second. The vertical velocity is always changing. It starts as positive 19.6. Then 1 second later, because it's accelerating at negative 9.8 meters per second squared, 19.6 minus 9.8 gives me 9.8 meters per second. Then it's 0, right? So the vertical component right here at the top, velocity in the y direction is equal to 0 at the top. Then it goes negative 9.8 and then negative 19.6. And so you can tell this is every 1 second for those velocity vectors. So that would be a total of 1, 2, 3, 4 seconds in the air, 4 jumps between those. And you'll notice that the path up is exactly equivalent to the path down, assuming no air resistance. The section up looks exactly the same as the section down, except that the vertical parts have become negative instead of positive for velocities. Okay. All right, so let's again look at that launch and motion of a projectile. And I just wanted to remind you that when we look at that initial velocity, you can break it down into its x and y components. The y component I could call v sub y 0. The textbook sometimes calls it v sub y I for v sub y initial. The physics cheat sheet, the AP physics cheat sheet uses v sub y 0 for like starting at time 0. Either way means the same. So if you see an I, it stands for initial, whereas in our AP physics class, we're going to use 0 for like time 0. In both cases, though, we start with this launch angle right there. That's theta. And then the vertical component is going to be v sub y 0, and that's going to be equal to v sub o sine of theta. And the horizontal component, v sub x 0, would be v sub 0 cosine of theta. So, and again, that's just based off of trig functions because sine of theta equals opposite over hypotenuse. The hypotenuse is v sub 0. The opposite angle in this case, here's my angle, so the opposite would be here, and that's the same as that, which is v sub y. Okay? So the sine one would be the v sub y one, the cosine one would be the v sub x. All right. Now, for objects that are in projectile motion, let's just kind of summarize big equations that you can use. When objects are in projectile motion, horizontal velocity is always constant. So the horizontal velocity, v sub x 0, is equal to the horizontal velocity the whole time, v sub x. And velocity is defined as the distance over time. So in this case, it's the change of x over the change of time because x is horizontal. And we are focused on horizontal velocity. For vertical motion, Vertical velocity changes due to acceleration due to gravity. So acceleration due to gravity is in the y direction, the up and down direction. And so now we include all of our equations that have acceleration due to gravity. And there are 3 equations given on your AP Physics equation sheet, all of which have acceleration in them. And listed in order: v sub y equals v sub y0 plus a sub gt, et cetera, et cetera, et cetera. I'm not going to read them out. So you'll notice that I've changed all of the x's on your equation cheat sheet to y's because it's in the vertical direction. So we're just going to use y for the vertical component. But you can see that on the cheat sheet, on the AP Physics cheat sheet here, everything is given in x's. So right here, that's an x, 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 and I've shifted them to y's because acceleration is vertical, right? So the x's and the y's are interchangeable. Just make sure you keep everything in the same dimension, right? So we're always going to use verticals, y's for verticals, and then it has to be all the vertical components. If we're doing a horizontal acceleration, like a car hitting the accelerator or hitting the brakes, taking off from a stop, or just not taking off from a stop, from a motion, then we would use the x versions. For acceleration due to gravity, because of it's in a vertical direction, up and down, actually down, then we're always going to use the y's. Okay. So let's stop and think. A 100-gram ball rolls off a table and lands 2 meters from the base of the table. A 200-gram ball rolls off the same table with the same speed. How far does it land from the base of the table? Okay, so it seems like the only factor that varies here is the mass of the ball. There's a 100-gram ball, and then a 200-gram ball rolls off the same table, same speed, right? So if it lands 2 meters from the base, the 100-gram ball, does the mass make a difference? Well, let's look at our equations. Let's see, horizontally, it's based on horizontal distance and time. Vertically, it's based on vertical velocity, acceleration due to gravity, time, vertical distance, acceleration due to gravity, time, vertical velocity, acceleration due to gravity. There's nothing in here about mass. So mass does not make a difference. If I drop 2 objects of the different masses, they should fall exactly together because acceleration due to gravity is the same on all objects on the Earth. Since it's the same table with the same speed, technically they don't say if they've moved the table to a different planet. If they move the table to a different planet, then it would land somewhere differently. But I'm going to assume that they kept the table on the Earth. And in that case, it would be exactly the same situation. So it would go exactly 2 meters because that's where the first ball landed. Okay, so the mass of the ball should not matter. All right, let's take a look at some trajectories of projectiles. So if you launch at different angles, and this one has an initial velocity, launch velocity of 100 meters per second, so same launching speed, you'll notice that if you launch really steep, well, let's start with if I launch totally vertically, right, then I would go straight up and then come straight back down, right? I would land exactly where I left from. So that would be the way to go the highest. But if you launch at some kind of an angle, if I launch at a 75-degree angle right there, or a 15-degree angle like right there, you'll notice I land at the same spot. So that's 15 degrees off of horizontal or 15 degrees off of vertical, lands in the same spot. Same deal with my 60-degree launch angle and my 30-degree launch angle. Those both land at the same position. And then finally, if I want to maximize my horizontal range, assuming no air resistance, I would launch at a 45-degree angle, and that would take me all the way out to 1,000 meters with a 100 meter per second launch velocity. Okay, based on that, let's stop and think. A baseball player is taking batting practice. He hits 2 successive pitches at different angles, but at exactly the same speed. Ball 1 and ball 2 Follow the paths shown. Which ball is in the air for a longer time? Assume that you can ignore air resistance for this problem. Okay, so right off the bat, it looks like ball 2 clearly goes further, right? Ball 2 looks like it's at maybe a 30-degree angle. Ball 1 is at maybe a 75-degree angle. But what controls the time that the ball is in the air? That's the vertical distance, right? If something goes higher, it's in the air for longer. So the one that that spends more time in the air is going to be the one that's at a steeper angle and goes higher. In this case, that is ball 1. Ball 1 goes higher, therefore it must take more time in the air because acceleration due to gravity is negative 9.8 meters per second squared. This should be getting repetitive for you. Acceleration due to gravity is the same on all objects. Because the acceleration is the same, higher means more time in the air. All right, circular motion, a new topic. So we're going to come back to this one in Unit 3, that's Chapter 6. But for right now, I just want to introduce this concept of circular motion and centripetal acceleration. So as I'm going around a circle, you'll notice that the magnitude of my velocity is always the same. So I'm not speeding up or slowing down, but I am traveling in a circle. So my direction is always changing. Because my direction is changing, my acceleration is always towards the center of the circle. Okay, so you'll notice that my acceleration is always towards the center of the circle. I could demonstrate this because from this one to the next one, which is here, all right, so if I add in that guy like that, where is it, like there-ish? I'm left with an overall towards the center angle. Now, these two are kind of too far apart, so really the angle should be right here towards the center like they're drawn. So based off of that, I can find the equation for centripetal acceleration. The derivation of that is in the textbook. What we're left with is acceleration centripetal in a circle is equal to the velocity squared divided by the radius. The radius, remember, is from the center to the perimeter, or in a circle, we call that the circumference. So that is the radius. Okay. All right, so that will be helpful. We're going to do a couple practice on that one in this chapter, and then it'll come back around and we'll really focus on it later. So which of the following particles has the greatest centripetal acceleration? Well, remember the equation is acceleration centripetal is equal to v squared over r. So I'm looking for a big V and a small r, right? That would maximize my centripetal acceleration. So in this case, I would do v squared over 1r, okay? In this case, it would be 2v squared over r, so that's like 4v squared over r, because 2 squared gives me 4. In this case, it's going the opposite direction, but it's still the same idea, v squared over r, right? In this case, it would be v squared over 2r, so that's 1/2 v squared over r. And then in this case, it's 2v squared over 2r, which is equivalent to 4v squared over 2r, which is equivalent to 2v squared over r. Okay, so I'm looking for the greatest centripetal acceleration. This one is 2. This one is 1/2. This one is 1. This one is 4. And this one is 1. The greatest of those is 4. So it would be B. I could also say I'm looking for a big V and a small r. And the one with the biggest V and the smallest r is B. So that's another easy way. All right. Let's do one final practice problem that puts everything together. Okay. Frogs with their long, strong legs are excellent jumpers. And thanks to the good folks of Calaveras County, California, who have a jumping frog contest every year in honor of a Mark Twain story, we have very good data as to just how far a determined frog can jump. The current record holder is Rosie the Riveter. I see what they did there. It's like Rosie the Riveter. It's a great museum, Richmond, it's close, you should go check it out. A bullfrog who made a leap of 6.5 meters from a standing start. This compares favorably with the world record for a human, which is a mere 3.7 meters. So frogs are much better at jumping a long distance from a standing start. Typical data for a serious leap by a bullfrog looks like this. Okay, so this is the actual part that we care about. The frog goes into a crouch, then rapidly extends its legs by 15 centimeters as it pushes off, leaving the ground at an angle of 30 degrees to the horizontal. It's in the air for 0.68 seconds before landing at the same height from which it took off. Given this leap, what is the acceleration while the frog is pushing off? How far does the frog jump? So there's two questions. Question number one is the acceleration of the jump. And then, so these are my needs. And then my second one is how far does it go, right? What is its total delta x? Okay, so for this one, I am going to start by breaking the jump down into, I think I'm going to solve for how far it goes first, because I have time data, I have angle data, and that would help me figure out where it's actually going. I don't think I need the acceleration in order to do that. So looking at my options here, I could use, I think I'm gonna have to break this down into horizontal and vertical components. So if I break it down into horizontal and vertical components, I can use, let's start with the vertical, because the vertical is what controls the time in the air. So for my vertical components, I'm given, and I'm just going to pay attention only to the in the jump itself. So I'm given an angle of 30 degrees. I'm given time of 0.68 seconds. And I'm given that the y0 is equal to the y final, which is equal to 0. It starts and ends on the ground, right? Okay. So given all that, I can plug in that the y component should be I'm going to use one of my equations, and I'm going to use y equals y sub 0 plus v sub y 0 t plus 1/2 a t squared. Now that would solve for my y velocity, right? My initial y velocity. And then once I have my initial y velocity, then I can plug that in and figure out my overall velocity and then use that to figure out the rest of it, I believe. So I know, plug this in, 0 equals 0 because it's starting and ending on the ground, plus v sub y 0 times 0.68 seconds plus 1/2 negative 9.8 meters per second squared, 0.68 seconds squared. Okay. So I'm going to do 0.68 squared times 4.9 So this is, so in order to get rid of this, I'm going to have to add plus 2.27 plus 2.27. So 2.27 equals v sub y 0 times 0.68 seconds, leaving me v sub y 0 equals, divided by 0.68, 3.33 meters per second. So that's my y vertical velocity. Now, my question is, how far does the frog jump? And that's an x version. So if I am looking for my x version, then I can take that y value and find my total velocity, and then use that to find my x velocity, and then use my x velocity to find my total distance. Yeah. Okay. Because all of it is going to be horizontal. Yeah. The parts that I care about are horizontal, but I have to find the vertical in order to find the horizontal. So as I throw this in then, now I need to know my x and my y components. I know that v sub x 0 is equal to v sub 0 cosine of 30, and v sub y 0 is equal to v sub 0 sine 30. I found v sub y 0 there. So if I plug that in, that gives me, let's see, v sub 0 equals v sub y 0 over sine 30, which equals to 3.33 over sine 30, which equals 6.6 meters per second is my total velocity. Now I can take that value, plug it in to that. So that ends up being equal to 6.6 cosine 30, which is equivalent to 6.6 cosine 30, 5.7 meters per second is my x component. So I'm getting there. Now I've got my x component of velocity. I have my time. So now I can finally go and find my horizontal distance. So to find that horizontal distance, I would say velocity in the x component is equal to the change of x over the change of time. Solve for x. So x equals vt, 5.7 meters per second times 0.68 seconds equals 3.9 meters. Okay, I actually found my change of x. That's 1. Nice. And just to be clear, I have no starting velocity horizontally. It's starting from a standstill, or it's a constant horizontal velocity. So I am okay just using that version. No acceleration horizontally. Okay, that puts me in great shape. Now I have a horizontal distance. I know that I need the acceleration. Now I'm solving for acceleration of the jump. So let me just recap what I've got. I need the acceleration in the x component of the jump. I'm given, what do I have in the x component? Delta x equals 3.9 meters. I'm given velocity 0 is equal to 0. Velocity final in the x direction is equal to, I just solved for that, in the x direction, 5.7 meters per second. So acceleration x v0, looking on my data sheet, that looks like the third equation. So that's going to be v sub x squared equals v sub x0 squared plus 2a sub x times delta x. Let's plug in all of my values. That gives me v sub x was 5.7 squared equals 0 squared plus 2 acceleration is what I'm solving for times delta x is 3.9 meters. Oh no, wait, wrong delta x. 3.9 meters is how far I went. But what I'm paying attention to now is in how much distance did that take place. And that goes all the way back up to extending its legs by 15 centimeters. So my change of position on the jump is 0.15 meters. That's where it gets tricky, is we've got two things going on here. So now I can use my change of position of 0.15 meters. But you know what? That change of 0.15 meters is on the diagonal. So instead of using 5.7, I should actually be using my total velocity because that's on the diagonal too. So I got to go back and shift it to 6.6 meters per second. See, this is where it's really important to go back and double check all my values, because that's going to make a big difference. And I have to keep my orientation the same. I was trying to figure it out horizontally because that's what I just solved for. But for the acceleration is not firmly horizontal. It's at the angle. So I'm going to do the acceleration at the angle and use all the angle data. In this case, the final velocity angled is 6.6 meters per second squared. And I do that push over 15 centimeters on the frog's legs. That's when the acceleration is taking place. So it's really important to keep those orientations accurate. Okay. 6.6 squared divided by 2 times 0.15 gives me 6.6 squared over 0.30 gives me acceleration in the x direction, which equals right around 150 meters per second squared. All right, I finally got there. Let me just go back and double check what I was being asked to do. I was being asked, let's see, what is the acceleration while the frog is pushing off? I got that at 150 meters per second squared. And then the second piece is how far does the frog jump? And I got that at 3.9 meters, and that seems reasonable. It is in the same scale as a human jumping, which is 3.7 meters. And then it's also a little bit less than the world record, which was what, 6.5 meters or something. So that feels reasonable. All right, I think we got there. Great job. And look, my class is showing up. So I will catch you next time. Good luck with those chapter 3 questions.